Assalamu alaikum. I would like to welcome you in our ninth lecture in M269, and today we are going to talk about new topics, which is mainly on graph. So we will introduce a graph and what kind of applications are using the concept of graph, and how the graph can be represented or presented. And every time we talk about graph, we talk actually about sum of nodes which are connected through vertices, and then the application of a graph. Actually, one of the most important application of a graph is how to visit each node in the graph one time, or at least in one time, or a maximum at one time, and that is possible through different types of algorithms. So here we're going to talk about the breadth first search and depth first search. These are two algorithms are used for tracing and actually traversing every single item in the graph. And then we will talk about, of course, the two types of searching. Actually, they differ in terms of the data structure they are using. Uh, so one of them is actually based on queue, and the second is based on stack. While we need to move after that to talk about the Dijkstra algorithm, which is responsible for finding the shortest path, and then we talk about the Kruskal's algorithm, which is also related to the spanning tree, and finding as well uh, uh, different actually subtrees, subgraphs from the original graph. So let's go through the slide, and starting with Euler. Actually, Leonard Euler, he is a Swiss mathematician. He was genius. At age of 20, he was actually got a scholarship from the Catherine First of Russia. It's like the Queen of Russia at that time. And he was studying at St. Petersburg in the Academy of Science. And then when he became 23 years old, he became professor of physics, and after 3 years, he became professor in mathematics. He has so many actually contribution in the two fields. I'm not going to talk about that much about it. Um, and actually, when he was 31 years old, he lost the sight of his right eyes, and then after that, he lost both eyes, the sight of both eyes, so became blind. He lived for actually almost 80 years. He has published so many books and journal papers. He's a great one. At that time, he actually, while he was in the academy, he heard about the Seven Bridge of Königsberg. There was a city, as you can see here. Let me draw it. So at that time, there was a city, and there was a river in the town, and the river actually divided the town into four lands, two separated lands, and the river was spanned by seven bridges, if you can see here in red color. So these are the bridges which are connecting the four islands, and so the people actually of the town, if they want to try to walk through the city, they have actually to cross all the seven bridges once and only once. So they are not allowed to visit or to use the same bridge twice. So that is actually the problem, how to use the bridges which are connecting the four lands, such that if you want to use the bridges, you should use them only once during the visit. So that's actually the concept of graph. So if you have some areas and they are connected together, so somehow you need to visit each node one time. So this process is called or known as traverse. So how I can go from here to this point to the third and then fourth, such that I visit each node only once. Of course, what I did here just now in this diagram is not eligible because I have drawn a line from this node to this node, which is not part of the diagram or the graph. We will talk about this, how they are actually connected with each other. So this is the seven bridges problem, and this is the graph representation of the problem, where we have some four places, and we have seven vertices. As you can see, now we have the vertices and the nodes, the edges. So this is called vertex, vertex A, vertex D, vertex B, vertex C, and the connection between the two vertices is called edges. So we have an edge from C to D and so on. So a graph, actually, if you want to match the Eulerian walk or the Eulerian network with a graph, then we say that a graph, if it has an Eulerian walk, then the number of odd degree vertices is either 0 or 2. What does this mean? Look at this diagram here. Now, each one of these vertices has some of the edges coming in and coming out. So for example, how many edges we have for this vertex? It's only one line. So this one has one. What about this one? It has 1, 2, 3. So this is a 3. Here, this one, 1, 2. So it's 2. This one, 1, 2, 3, 4. So it's 4. This one, 1, 2, 3. So it is 3. So in total we have three vertices of odd degree. So we call each number here as a degree. So the degree of this vertex is 2. The degree of this vertex is 3. So it is actually violating the rule here. So if a graph has an Eulerian walk, then the number of odd degree vertices is either 0 or 2. Here we have 3 vertices with odd degree, which means that this is not Eulerian walk. So as a Eulerian circuit, we call it Eulerian. So we have two terms here. We have the circuit and the path. Euler circuit is actually in a graph is a symbol circuit containing every edge of the graph. So it's just a symbol graph. Symbol circuit is a graph or symbol circuit, and it contains all the edges of the graph. And Euler path in a graph is a symbol path containing every edge of the graph. So what does this mean? Now, if you can see here, let's discuss what do you mean by symbol graph. Now, by looking at this graph, this is called symbol graph because it has no cycles and no multiple edges from each vertex. If you look at this one, we can see here we have circle, a loop, and here we have multiple edges between the two vertices. So this is called symbol because it has no loop and only one vertex is connecting every two vertices, or one edge for connecting any two vertices in the graph. So this is called symbol graph, and this is not simple graph. So this can be Euler circuit and Euler path. Of course, a path is in the circuit itself. So this is called undirected graph, where it has a set of vertices, 1, 2, 3. This is the group V, and we have the set of edges 1 to 2. This is one edge, as you can see it here, defined here. 2 to 3, another edge. So 2 to 3 or 3 to 2 doesn't matter because this is undirected, and 1 to 3, another edge. So what we mean here is that we have some directed and indirected, or sorry, not directed graph. Here we have not directed graph. Why? Because there is no arrow to show whether the edge from 2 to 3 or from 3 to 2. Unlike the situation or this graph where we have clear direction from node to another. So this one we call it directed graph because the edge has a direction. So if we are talking about directed graph, there is a difference between saying from 3 to 2, or we say 2 to 3. So these are two different association. So this is incorrect, and this one is the only correct one. Let's talk more about some of the terminologies. We have the endpoint of the edge. So this is an edge, for example. This is called an edge A. So A has two endpoints. Any edge has two endpoints. So the endpoint of A is U and V. And also the edges incident on a vertex for the vertex itself. So here for example, the incident of vertex X, or this is very long one. Let's talk about, for example, Y. The incidence of vertex Y is G F. The vertex of W, the incident of vertex or on vertex W is F E D C. So these are called incidents on a vertex. Degree of vertex is how many edges do we have, number of edges coming in or out the vertex. So here, for example, you can see for X, it has 1, 2, 3, 4, 5. So the degree of X is 5. Also, we have parallel edges. Parallel edges, for example, for these edges H and I, they are parallel, يعني متوازيات. So they are running at the same time. So we call them parallel edges. And we have the self loop, where, for example, Z, the vertex Z has the edge going out from Z and coming back to Z again. The path, we have simple path. Actually, the path is the visiting, how the sequence of the vertices and edges we are visiting. We start with a vertex and we end by another vertex. So start with the source and end with the destination. And every time we need to go from one edge, one vertex to another, we have the edges. And simple path is actually a path that all vertices and edges are distinct. So for example, we have a path from V here, starting point, and Z is the ending point. So if you want to go from V to Z, we can go from V to X, and then from X to Z. So we can say it in this way. From V through edge B, so B, then we arrive X, then through the edge H, we arrive Z. This is how we draw or write the path. So this is called simple path because every single actually edge and vertex is not repeated at all. It is only mentioned once. Now, once we start repeating some of the vertices, as we can see here, from U, W, Y, X, W, V. So W vertex has been repeated twice. As you can see here, we go from U through C to W, and then from Y to W again, and then to V. So W vertex has appeared twice. So this is not a simple path. That is to distinguish between simple and not simple paths. Of course, also the number of vertices, also called the order of a graph. So, how many vertices do you have in the on the graph? It represents the order of the graph, and it is denoted by the letter N. And the number of edges is called the size of the graph. So here in this diagram, for example, we have 1, 2, 3, 4. So the order of the graph is 4, and that is denoted by N equal 4. And for the number of edges we have 1, 2, 3, 4, 5, 6. So we have m equal 6, which is number of edges in the graph. So the graph, any graph, can be represented using two types of matrices. It can be either using the adjacency matrices or incidence matrices. When it comes to adjacency matrices, it's a matrix. It is actually based on the how adjacent are the vertices. So the key points here in adjacency matrix is the vertex is itself. Once we move to the incidences, it's actually here we care more about the edges. So let's see how different is these two types of matrices. So let's assume that we have this diagram or this graph. It has the vertices group of V, U, W, and Z, and they are connected through the set of edges E, G, F, and H. So for all edges and vertices in this group, we will create a matrix. It depends on how many vertex we have. So let's say we have here 1, 2, 3, 4 vertices. So we will create a matrix of 4 columns and 4 rows labeled from 0 to 3. So each row represents a vertex. So this is a vertex U. The second one is vertex V. The third is W. The fourth is Z. And now every time we check the vertex, and also the column itself is for the vertices. So every time we need to check the relation, if there is an edge associated between the vertex on the row with the vertex on the column. So the first question is how to enter 0 or 1 here. It depends on whether there is an edge between U and U. So here is U and here is U as well. So is there in this diagram an edge from U to U? No. Since there is no edge, so we put 0. But from U to V, which is V number 1, so from U to V, yes, we have 1, which is E, so we put 1. Also from U to W, which is number 2, yes, we have, so that's why we have 1. But from U to Z, we don't have any link, so or edge, so we put 0. So by doing this, for every single row, we will come up with the adjacency matrix. And this is actually the way of filling it up with zeros and ones. It's called the old-fashioned version of the adjacency matrix. Now, instead of doing this or writing 1 and 0, we can just directly write down the name of the edge itself. So instead of writing 1 and 1 here in the first row, we can specify it explicitly. So we say, yeah, from U to V, we have one edge and it is labeled by E. And this one is replaced by G, because this is from U to W. So these two representation is called adjacency matrix. But when it comes to edges, now the rows in the incidence matrix, the rows represent the vertices and the columns represent the edges. So here we want to know if a particular edge belong to this vertex or not. So here when it comes, for example, for U, let me clean it up. So here we have U. The vertex U is actually associated with two edges. It is associated with E and G. That's why you can see E and G is 1, 1. For V, it is associated with E and F. So that's why you can see in E for V and F, and the rest are 0. So here we actually checking whether or examining whether a particular edge belongs to a particular vertex or not. So by doing this, actually we are actually representing the same graph but in different presentation. And for the graph ADT, the abstract data type, you can find it actually in lecture 9 dash code part in the GCC, on the GCC page. So in that is actually the implementation of the graph abstract data type using Python language. So you can see here a lot of a set of functions that is associated with graph ADT, including checking how many vertices we have in the graph, and what also vertices do we have. Give me back the list of vertices, count the edges and return for me all the edges, and get a particular edge between two vertices, and so on. Now, since we are now familiar with graphs, then we'll start talking about how to search and how to traverse each element and each vertex of the graph. And we will focus mainly on two well-known algorithms, that is called breadth first search and depth first search. In the breadth first search, actually, it is in this structure, this algorithm consider the queue data structure, where every time we visit a node or we visit a vertex, we will push it to the queue. And once we finish one level, every level in the graph itself, then we will pop the item from the queue. We will have an example actually which can show us how exactly we are visiting the nodes in the graph. So let's say we have this diagram. This is the initial diagram. We will start by visiting the node. This is the root at level 0. So we start by visiting the node A, and then from A we can reach to B, and we can also reach to C, and we can reach to D. So we will push P to the Q, and then push C again, and then push D. See, we are pushing 3 elements because these are actually that can be traversed from the root A. So we have A again. From A we can reach to 3 vertices: B, C, D. See, so we will push B to the Q. So this is the Q, and then we will push C to the Q from the end of the Q, and then D to the Q. So in these 3 steps we will have B, C, D. Are there any more vertices to visit from A? In this case, no. So the next step is, since there are no more points, so we will go back to the previous, or to the top of the queue. What is the top of the queue? It's P. So we will put the pointer back to B and pop it out from the queue. So we are dequeuing B from the queue. So now we have visited A and B, and then now from B we can go to E, only to E. So push, or push or dig in Q E to the Q. So that's why we can see now E here. After that, from E we cannot go anywhere. There is no other levels down from E. So at that case we have to go back to the top of the queue, which is C. So pop up C. C is labeled as visited. So we will have now this diagram after we pop or dequeue the top of the queue, which is C, from the diagram. So we have it in this way. So from B we go to E. Since E has no more nodes below it, so it cannot go anywhere. So we have to go back and check what is the top of the queue. The top of the queue is C. So go back to C, pop it out from the queue or dequeue it, and now we have D and E in the queue. Now from the D and E, what is the top of the queue? Is D. So we put the pointer D. So from D, where can we go? We can go to F. So we include or enqueue F to the queue. So we're supposed to have D, E, F. Now from F we can go nowhere. So remember, we have A, B, C, and now since from F we have nowhere to go, so check the head or the top of the queue. We have, so pop D out from the queue, enqueue it. Dequeue it. So we dequeue D from the queue, so become the output. Now the queue will looks like this, only E and F. So the pointer will back to E. So now the top of the queue is E. From E it is visited, so pop it out from the queue, so it will be popped out, and then the pointer will be shifted to F. So F is visited before, so pop it out from the queue. So now it is dequeued, and the output is A, B, C, D, E, F. And by this we are visiting every single vertex in the graph. So the main idea is, once you arrive to a node, from that node you have to enqueue all possible nodes that can be visited from X. So if you remember, when we are here at B can be accessed or can be used to access E. That's why we pushed E or enqueue E to the queue. So every time you reach to the point where F or E has no other points to visit, so back again to the top of the queue, dequeue it from the queue, and then move to the next item in the queue. So by this we are actually traversing every single element in the graph. So that is called the breadth first search. The next one is the depth first search, and that is actually based on the stack data structure. How does it work? Let's assume we have this graph, and now we want to start from A as a root. So from A we have 3 nodes to visit: B, D, E. So let's start alphabetically. We visit from A, we can visit B. So push A. After, of course, pushing A as a root to the stack, we push B to the queue, to the stack. Now we have A and B in the stack. Now from B, after we push B, we push the second items that we can visit from B. So from B we can visit C. So from here, after we push the B, we go to C. So push C to the stack. Now in the stack we have A, B, C. Now the pointer is moving in C. So this is the pointer now, A, B, C. Now from C we can go to D, and we can go to E. So we have 2 options. We go to D or E. Alphabetically we will visit D. So push D to the stack. That's why we have A, B, C, D now. D is pushed to the stack. Now remember to label the elements that have been visited. Now also D is visited. Now back to the D. From D, can we go anywhere? No. No more arrows or direction for any other nodes or vertices in the graph. So what we have to do is to pop the element D from the stack. So D is popped. So by popping D, now the pointer will move again to C. Now the top of the stack is C. So from C, we have already visited D. This one is visited and this one is visited. So where can we go else from C? We can go to E. So push E to the stack. So E is pushed again to the stack. So now we have A, B, C, E. Now we reached E. In this case, E is the end of the graph. So no more lines here. So from E we will go back to, let me move it. Okay, from E we can go back to A, but A is already visited. Here, by the way, there is a line. So A is visited, so pop up E from the stack, and then C is already now visited. No more unvisited nodes. Then we pop out the element C from the stack, and then we move the pointer to B. No more element to visit. So pop out the element B from the stack, and then we reach the A. So we're visiting A, and it's be popped out from the stack. So by doing this, we are visiting the elements of the trees. So actually, both algorithms will lead us to the same order of traverse, except for the elements, of course, E and F. So where we visited here in the DFS, we visited F then E, but here we visited in the breadth first, we visited E than F. So that is the only difference between them in terms of visiting. But at least that is not important which one is visited first. What is important is that each item or each vertex is used or visited only once. Now, as we mentioned earlier, we said, for example, here somebody might go to A, B, E, C, D, E. Somebody else might go by using different path. So they might choose this path, for example. So they can choose A, B, C, D, F. This is another path. So as we said, graph has so many applications, and one of them is actually like the one used for connecting cities. So if you have a salesman who is responsible for visiting multiple regions, okay, something like this, and he's somewhere here, he is located here. So from which point he should start and what is the next. So if he started from here because he's closest to this area, shall he go here or here or here or here or there? So there are so many paths that he can actually use for covering this region. But the optimal solution is actually finding the shortest one, finding the shortest path. So one way of finding the shortest path is by using the Dijkstra algorithm. So it is responsible for finding the shortest path based on the weight. So we assume that each path has a weight, and every path between two pair of vertices has a particular weight. So actually, without a weight, we cannot judge the shortest path. So we can show you, for example, if I have here, this is Riyadh, and here we have Jeddah, and I have here Dammam. One way of representing weight is that I can go from Riyadh to Dammam in two directions, of course. The weight is 400 kilometer. So this is actually a weight. From Riyadh to Jeddah, I can go by 1000. So this is the weight of this way, of this road, of this path. From Dammam to Jeddah, I can go by, for example, 1200. This is an example. So this is the weight. So if you are here in Dammam and you need to visit Riyadh and Jeddah, shall you go from Riyadh to Dammam and Dammam to Jeddah? Sorry, from Dammam to Riyadh and from Riyadh to Jeddah, or you go from Dammam to Jeddah and then to Riyadh. The shortest path said, if you are in Dammam, then from Dammam, Riyadh, then Jeddah, this path will cost you 400 plus 1000. So 1400. But if you choose to go Dammam, Jeddah, Riyadh, then it will cost you 1200 plus 2200. So what I mean here, the cost of the path here, which is the weight, will judge or will help you to find the shortest path. And Dijkstra 1 algorithm is one of them actually. So let's have a look on how this algorithm works. So here we have a graph, and we need to assume that we have a source and destination, and let's say we want to go from A to G. This is an example. So from A to G, we will start with actually checking what we can visit from point A. But before that, let's have a weight for every single vertex. So starting with the source, which is 0, because we're starting from A, so it has a weight 0. And at the beginning, we will say that there is infinite way from A to any other node. So that's why we have infinite here as at the beginning. So it is actually going to be reflected on this table, which shows the iterations. Now every time we move from one vertex to another, we have, which is called an iteration, we have to update the weight of these vertices. Now starting with A, which can go to actually two nodes, B and D. So from A to D, the weight is 1. So we are going to update D1, and from A to B, the weight is 2. So now the weight of B is 2. So again, let's clean up the graph now, since we know the notations. And we do it again. From A, we can go to B and D based on the direction of arrow. See, we cannot go to C because the direction is actually from C to A, not from A to C. So based on this, let's go from A to D. From A to D, the weight is 1. So this infinite will be 1. And from A to B, the weight is 2. So we will update the infinite to have a weight 2. And it's going to be actually updated here. So in this iteration, B has a weight 2, and D has the weight of 1. And the rest is the same. Now we have two new updates, which is the distance to B and the distance to D. Now we back again to the root, which is A. Now A has two options, either to go to B or to go to D. And since Dijkstra algorithm, it's a greedy algorithm, so it's looking for a winning all the time. So based on the two options, A can see that the shortest path is to D because it has the minimum weight. So we will label A as already visited, and then we go to D. So we choose D as the next point. Now once we arrive D, from D we have to check what points or vertices we can visit. So from here we can visit E, G, F, and C. Of course cannot be because the arrow from B to D, not from D to B. So now let's update the weight. Now the weight from D to C is 2. But to reach to C from D, you have to carry out your weight as well, the weight of 1. So the weight of C will include 2 plus 1, which is 3. And the weight of F will include 8 plus 1, so it is 9. So we will update it to 9. Of course, whatever I write here, it has to be updated on the table, similar to what I did in first iteration. For G, it is 4 plus 1, so it's 5. And for E, it is 1 plus 2, which is 3. Now we back to D. D has now a weight for every single path. So which one to choose? In this case, it will choose the less one. Since we have two options, sorry, let us move to the second one. So here is, as I mentioned, this is the 3, and his A1 and plus 9 is 9, and here we have the 5, and this is the 3. And of course it is updated here on the second iteration. Now we have two options. Now we back to D. From D we need to decide where to go. And from B we can see that from here. Now D will look at the direction this way. Okay, I have multiple paths. I have from D to C, from F, G, E. But you have to remember that you have not visited another node from the root. So you cannot go deeper unless you finish the upper level. So in this case, I will not go from D to any other node below it. I will go back and check if there is any unvisited node above the D. So here we have in the root, you remember, in the root we have two options. Either we go to B, from A to B, or we go to D. So we covered A to D, so let's go back again to A. From A, I still can see only one node not visited, which is B. Now let's update the weight of the connected nodes. So in this case, B can go to E and can go to D. So from B to D, it will carry 2 plus 3, which is 5, and B to E, 10 plus 2, which is 12. So, of course, I'm not choosing 12 because here this is 5 and 12, but is not going to update it because it is more than the current one. Remember, don't update here, don't update it unless it is less than the current one. So 12 here, it's not considered because it is bigger than 3. So don't update the graph. So we'll keep it as it is, 3. And then from E, we reach to E. From E, we can visit one node only, which is G. Right? So in this case, we back again to the node, the original. See, I cannot visit any node below E unless I finish all the other nodes from the original. So I'll go back to D. So from D, you have to choose. I already visited E, I visited B, I visited A. What is rest? I have 3 options more. Either I visit C, which has weight 3, or I visit F of weight 9, or I visit G of weight 5. So in this case, the minimum is 3. So from D, I will visit C. So the next point is C. So from C, I can go only for 2 options. Either I go to A, or I go to F. A is already visited, and the weight is 4, which is greater than 0, so I will not consider it. So I will go to F. So F3 plus 5 is 8. So it's going to be, of course, 8, which is the same distance. So there is no more, it will be updated. Last time F was 9, see? Because it came from D, so it become 9. But when I visit F from C, it become 3 plus 5, which is 8. So that's why I updated the weight of F and make it 8. Now this one visited, 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 and now F is visited. So from F, I cannot go anywhere. So I have to go back again to C, and then I have to go back to D, and then from D, I can visit G. So from D has a weight 1, plus 4 is 5. I keep it as it is. So by doing this, I'm actually visiting all the nodes and finding the shortest path between them. But by the way, yes, there is one more node. When I reach G here from D, now G can go to F. When I check the weight of F, I found that F, I can reach it from G of a weight 5 plus 1. So 5 plus 1 is 6. So the new there is another update for the weight of F. It was initially 9, then from C I make it 8, and then from G I make it 6. So the shortest is 6. So based on this, from A to G, what is the shortest path? Of course, the shortest path is to reach G is from D and then from A. So it is A, D, G, which I can reach it of a cost of 5. So that's it. That's how I find the shortest path um, of a graph using the Dijkstra algorithm. And so every time you need to check the weight and calculate a new weight for every single vertex uh, in S. And remember, we don't update the weight of a vertex unless it has a new lower value or lower cost, we call it. Now, what is the problem of Dijkstra algorithm? Dijkstra algorithm is greedy algorithm, as we mentioned earlier, where it can see only the local optima of the solution. The local optimal of the solution means, let's assume that we have this circle, and inside this circle we have smaller circle. Okay. Now, let's say we have the maximum price in this circle is 100 real, and the maximum price for this circle is 1000 real, and the maximum here is 1500 real. So if you are here, if you are within this circle, you can see only, because you are greedy, you are looking only to get the 100 real. That is the maximum you can see in your area. So that's why it's called, this is the local optimal. So the local optimal for from your perspective, because it's your local, so it is 100. But if you are looking globally, so we can see the global optimal, which is 1500. So for greedy algorithm, they can see only what is available right now. That's why we call them, they fall in local optimal. But it's hard sometimes to reach to the global optimal. If you want to reach the global optimal, then you might lose in the beginning. So you might lose in the beginning, but you might get winning at the end. So, but if you are looking greedy, you just want to get the price now. Like, it's something like if you have a kid and you tell your kids, do you want, for example, a small toy today, or you want the big toy after 1 week? So the kids will go for what is available now. If I can get one now, one small toy now, it's much better than getting a bigger one on next month or next week. So if they are greedy, they will look for the current price, the small one that they can see right now. But if they think globally for global optimal, then they should wait for 1 week or 1 month to get the bigger one. And that is the same thing for greedy algorithms like Dijkstra. Now, moving to the other type of graph, which is called the minimum spanning tree. So a tree, it's actually, just to remind you, a tree is a connected, directed, a cyclic graph. It's a cyclic graph. So a spanning tree can be a subtree. A spanning tree is a subgraph or a subtree, which means the constraint of the tree. And the minimum spanning tree is a spanning tree with the weight less than or equal to any other spanning tree of the graph. Let me tell you what I mean by spanning tree. Let's have this as a graph. So we have A, B, and C. And they are actually forming a tree. This is a a graph which include these different uh, vertices. Now, what do you mean by spanning tree? Spanning tree, it must any spanning tree should be actually a graph which include all the vertices, but it must not be actually a cycle. So there should be no cycle. What I mean is, this is a subtree or spanning tree. This is the first one. See, it is the same order, A, B, and C. So from A to B and B to C, this is one spanning tree. This is the original. This is spanning tree. Another spanning tree might be like this, from the same graph. Another one might be like this, from A to C and C to B. So this and this and this are called spanning tree. What is minimum spanning tree? It's the spanning tree which has the minimum weight. So if you have two spanning tree which has the same weight, then both of them are called the minimum spanning tree. Now, finding the minimum spanning tree can be used is actually using the Kruskal's algorithm. So we will work actually here with edges, not with nodes, not with the vertices. So first sort the edges by increasing edge weight, and then select the first V minus 1 edges that do not generate a cycle. So here we need to find actually this is another type of greedy algorithms which used for specifying the minimum spanning tree. This is an example. This is a undirected weighted graph where we have a list of vertices or nodes, and they are connected through different edges. See, note that we have a cycle here. H is connected with itself using a cycle of weight 8, of course. So in step 1, we need to remove all loops and parallel edges. So this is the first step, removing the loops and parallel edges. Second one is actually uh, the arrangement. We arrange all edges in their increasing orders. So from the smallest to the highest in ascending order, and then add the edges which has the least weightage by actually to the graph, and as this is actually illustrated in our next example. So after we take out the cycles, see, this is the cycle here, H, it is now deleted. H has no cycles. And actually here we have the link from E to G as a parallel link. It is also taken out. It is deleted from G to E. So in this case, what else we have? Yes, so that's all what we have. So step 2, we have to start arranging the edges. So this is a table for sorting the edges. Now starting with the minimum. The minimum is from D to E because it has a weight 1. So we write here DE 1. And then we have from D to G. See, we are focusing on edges now in this kind of algorithms. So D to G has a weight of 2, so that's why we have 2. And then we have from E to G, which is the 3. And then we have C to D. C to D. By the way, here was a mistake. This link should not be taken out because it is not parallel. I thought it is parallel with G and E. The link is between G and D, so E and G is not taken out. And then from C to D we have the other one, another 3, and also we have from C to F 3 here, and we have from GH also, GH you have 3 here, so this is another 3, another 3. These are all taken. And then next is 4. 4 we have multiple one. We have here 4, B to E, C to B, F to B, H to B, and you can see them all here. And then number 5 we have A to H, here is it, and D to F number 6, so here's from D to F, and then A to B, which is 8, and then A to F with which is from of weight 10. Now we have already solved them in increasing by increasing edge weight from the smallest to the largest. Now step 3 is to add the edges, sorry, which has the least weight. So the least is actually just mark them different color. I will change the color as well. So this is very simple. We have from D to E, which is 1, so I draw a line from D to E. Next is from D to G, so I will go from D to G, it will be here. And then from E to G, and from from E to G, and from C to D, and from G to H. So I have a weight from G to H, so I can go from G to H. And then after that I can go to from H I can go to B. This is a spanning tree. And then from B I can go to multiple ways. I can go to F, I can go to C, so I can choose, for example, going to okay, let us go to H, we finish it. I can go to F, and then from F we can go to A. So this is a spanning tree. See the D. Okay, and this is by the way, this is what I mentioned just now, a spanning tree, but that is not the minimum spanning tree. Another way of telling you this, let me explain before we go to the minimum. Another way, I can go from, let me clean it up, I can go to E to D, and then I can go to from D to F, and then go to B and go to A. This is another spanning tree. But now I want to go, I need to find the minimum spanning tree, which include all the vertices and has the less weight. So from E, D and E, so I go E to D, and then from D to G, because it has the less. Now the next is, I am now already in G. Now if I want to go back, in this case I want to go to the the spanning tree property does not hold in what we shall consider not to include the edge in the graph. So here what we mean is, so what is important here is to make sure that every time we check an entry from the table, it is actually not violating the rules or the restriction of the spanning tree properties. So here when it comes to EG, it is of actually of weight 3. So EG here, this line is actually, if we add it to the spanning tree, then it is actually violating the rules and the restriction of the spanning properties, because it become a cycle. See, become C, D, E, and G. So it's a cycle. So we should not include this this edge. So that's why we put X here. Now C to D, it's a weight of 3. So does it violate the rule? No. So include it. So here we include C. Now the next is GH. GH is actually of type 3. Remember, we need to visit every single vertex in the spanning tree. There is no spanning tree without including all the vertices. And what we are looking for the minimum also, the minimum spanning tree. So from C, now next we have GH. The GH is here, this link. So if we add this link, does it violate the rule of the spanning tree? No, it makes no cycles or anything. So yes, we include it. Then CF. CF is here. So does it hurt or violate the rules? Of course no. So include it. And then next is BC. So BC is here. So if we add this line, does it violate the rules of spanning tree? No. So go ahead. Now BE. Now here, where is the BE? Is here. This is the BE. If I add this link, then there will be a circle. See, a cycle here. Afwan. It's not a circle, it's a cycle. So it's violating the rule. So X. And BF. If I add a BF here, does it violate the rules or not? By adding BF of weight 4. If you add a BF, see. Remember that I have a link here. So if I add BF here, then I will have a cycle. So of course, it's not considered. So I will have another X for BF. And then I'll move to the BH. So remember now, BH is here. So if I add a BH here, I will have another cycle. See, here it is. This is another cycle. So BH is also not included. I exit. AH. If I add the link between A and H, it will not violate the rules. So it's correct. I will add it. So it become red. And then by this, I am visiting every single node and vertex in the graph. So I will not consider any other um, links. So by doing this, this is actually the spanning tree, and that is the minimum spanning tree that I can generate from that graph. What is the cost? What is the cost of this spanning tree? It is 5 plus 3, which is 8, 8 plus 2, 10, 10 plus 1, 11, 11 plus 3, 14, 14 plus 4 is 18, 18 plus 3 is 21. So the total cost is 21 for this particular minimum spanning tree. So in general, spanning tree is a tree that include all the vertices with the minimum number of edges. So to do this, first you have to delete or take out all the cycles and the parallel edges. Second, put a table which include all the edges weight in ascending order, and then consider marking the nodes that has actually the same the minimum weight, and that does not violate the rule of spanning tree. So the rule is, whenever you include an edge in the spanning tree, make sure it does not create a cycle or a loop. So in terms of the time complexity, the Dijkstra algorithm complexity is actually of n to the power 2, and it's actually if it is implemented using adjacency representation or matrix representation, but if it is represented using heap binary heap, then it will be reduced to log n, e log n. For the Kruskal algorithm, the time complexity is e log e, or you can consider it n log n. Of course, we have different values for different analysis, how long it takes for sorting, because it has sorting, and then you have to take out the search for loops and so on. So every single process, it has its own cost. In general, it is of E, where E is the number of edges and V is the number of vertices. So here is OEL. Log E means it is, or log V, it is based on the number of edges and number of vertices you have in the graph. So by this is actually the end of our class, and I'll be glad to discuss any issues that raise while reviewing this lecture. Thank you for your attention. Assalamu alaikum.